Good day. In today's discussion, we will be discussing about estimation of the mean and proportion. So this is taken from our textbook, Introductory Statistics and Addition by Prem and Mann, Chapter 8. So let's have first our definition. So the assignment of values of a population parameter based on the value of a corresponding sample statistics is called the estimation. So although we do know what estimation means in contextual usage, but for statistics, it's assigning a value to a certain population parameter using your the sample statistic. So if you remember what a sample statistic is, it's basically a parameter of the sample. So for example, it's the sample means or sample median or sample standard deviations. So that is your sample statistics. And if we use this sample statistic to estimate our population parameter, basically we call that method estimation. So the value assigned to a population parameter based on the value of your sample statistic is your estimate. And the sample statistic used to estimate the population is your estimator. So here is the general steps on how to estimate or rather how to do estimation. So first, you need to select your sample, collect the information from the sample, and calculate the value of your sample statistics. And then after that, we are going to assign the value using the sample statistics value, we are going to assign a value to the corresponding population parameter. For example, if we have for sample statistic, we have our sample mean. We are now, based on our sample mean, we are going to estimate or assign a value to the population mean using this sample mean. So the value of a sample statistic that is used to estimate a population parameter is your point estimate. Now we call it a point estimate because it's a single, or it's basically a one, because it's a value for a sample statistics. For example, sample mean, it's a one digits, one point, or one data, one value. So it's a point estimate. Now, having just a simple point estimate is not really quite accurate. So rather than doing point estimates, in order to properly provide information on the population parameter, we usually do interval estimation, whereas the interval is constructed around the point estimate. And we assume that within this interval, or rather this interval contains the corresponding population parameter with a certain confidence level. So, uh, going back, so remember, the sample statistic value that we are going to use to estimate out the property, the parameter of the population is your point estimate. And this is not so accurate, or it's not there is actually prone to errors. So that's why we do interval estimation. We expand the point estimate to a certain range or interval, where we would say that the population parameter is within this interval. So the range of that, the number we add or subtract to the point estimate, we call it the margin of error or the maximum error of estimate. So for example, here is your population. So this is your population mean, and this is the sample mean, the mean we got from our sample. And so as you can see here, the sample mean is not really equal or not really the same as or equivalent to the population mean. And that is why when we do estimation, or basically when we do estimation, rather than saying that the population parameter, the population mean is 2,970 based on our sample. Rather than saying that, we just say that the population parameter falls within a certain value that we construct around the point or the point estimate. This is our point estimate. This is our true sample, true population mean. So we construct your interval, and that interval is this range. So we add or subtract values from our point estimate. We add or subtract values here, so that we can say with confidence that the true population mean is between the values of 2,630 and 3,300 10. So this is your interval estimation, and which is actually true because our true mean or the true population mean really falls between these values. And the range, this value that we add or subtract to the point estimate is your margin of error. So each interval is constructed with regard to a given confidence level. So the interval is based on how confident we are in our estimation. For example, if we want to have a high confidence, we were going to expand our interval. If we have low confidence, usually the interval is has a less width. So the interval constructed with regard to a given confidence level is called the confidence interval. The confidence level is the confidence level is given as the point estimate plus minus our margin of error. So the confidence level associated with the confidence interval, it states how much confidence we have that this interval contains the true population parameter. And the confidence is denoted by 1 minus alpha times 100%. For example, it's 95% confident, it's 97% confident, it's 99% confident. So this is our confidence interval. So there are three cases on how we estimate population mean, provided that actually there are actually two cases on estimation of population mean. When we know the population standard deviation and when we do not know the population standard deviation. But first, let's look at how to estimate the population mean if we know the population standard deviation. So if we know the population standard deviation, we have three possible cases. So the first case has, of course, we know the population standard deviation. We have a small sample size, and by small sample size, we can say that n is less than 30. Now, the number 30 is more or less arbitrary and is a rule of thumb rather than an actual law. And then the population from which the sample is selected is approximately normally distributed. So there's no skewness, skew to the left or skew to the right. No, it's not. It's generally follows the standard normal distribution. A second case is that we know the population standard deviation, but we also have a very large sample size, which is we consider a large sample size is greater than 30. And the third case is again known population standard deviation but small sample size, and we do not have a normal distribution. So during these cases, what should we do? So if we know this population standard deviation, there are three possible cases. You have a small population but you have an approximately normal distribution, or you have a large population. When you have this scenario, what we are going to do is we can use the normal distribution to estimate our population parameter. Now, for the third case, we have a small sample size and we have a population that is not considered a normal. It's not normally distributed. It doesn't follow the bell-shaped curve. So we are going to use non-parametric methods. In this lecture, we will be just discussing about cases 1 and 2. Now, let's talk about population, the confidence interval. So if we have a known sigma or known population standard deviation, so our confidence interval, the n% confidence interval, so 1 minus alpha can be 99%, 95%, or so on and so forth. So if you have a certain percent confidence interval for knowing the population means, so under cases 1 and 2, our interval is, this is our point estimate, sample means plus minus. This is the amount that we are going to add or subtract to our point estimate to get our confidence interval. Whereas our sigma sub x bar is the normalized value for the standard deviation. So this is standard deviation divided by the square root of our the number of members in the sample. So this is the normalized standard deviation. So the value z here that we are going to use is from our normal distribution table. And by the way, this confidence interval is rather pertains to the area under the curve. So the margin of error for the estimation of our population parameter or population mean, this is E, is a quantity that is subtracted or added to the value of x bar. This is our sample statistic. or this is our sample mean, to obtain our confidence interval. That's our margin of error. So this is our margin of error, the amount we add or subtract. So here is the curve for the 95% confidence level. So when we say we are 95% confident, that is 1 minus alpha, whereas alpha here is 0.05. So when we have an alpha of 0.05, that's a 95% confidence level. And when we say 95% confidence level, this pertains to, if this is from our standard normal distribution graph, we have the 0.95 pertains to the area under the bell-shaped curve in the middle. So you have here, basically we are saying here that the population parameter, the population mean, is within the area here, that is 0.95 area, 95%, or rather have an area of 0.95. And the tails here are the extreme end. So this is 0.0, because 9.95, 1 minus 0.95 is 0.05. So divide by 2 from the two ends. So 0.025. So this is our confidence level. So basically, we are basically have a higher chance, or our confidence, the true population parameter that we are trying to estimate, has a high chance of being within. We are 95% sure, we are 95% confident that the true population parameter is within this area of 0.95. That's actually what it means to have a 95% confidence level. And then this is the area with the tails. So here are some values commonly used. So if you are into reading research publications and looking at statistical confidence level, you would usually see a confidence levels of 95% or even 97%. And if it's usually a clinical trial for small sample, it's 99% confidence. So it's these are the different these are the usual confidence levels that we are using. It has also its application in analysis, analytical skills, and research. Okay, let's have an example. A publishing company has just published a new college textbook. Before the company decides the price at which to sell the textbook, it wants to know the average price of all such textbooks in the market. So the research department at the company took a random sample of 25 comparable textbooks and collected information on their prices. This information produced the mean price of $205 for this sample. Basically, our sample mean is 205 from our sample of N25. N is equal to 25. It is known that the standard deviation of the prices of all such textbooks is $47. Now, this is our population standard deviation, and it follows the population. A population distribution is a normal, or rather is approximately normal. So that means this is case number 1, whereas you have your less than 30 samples and you have a normal population normal distribution and a known population standard deviation. Now, what we are looking for the point estimate of the mean price, and what is the interval of 90% confidence interval of the mean price. So the mean price should fall within a certain range, and we want to be 90% confident that the true mean price is within the range that we have constructed using our point estimate. So the point estimate is basically just the same as our sample statistic. And our sample statistic is our sample mean, and our sample mean is $205. This is from the statement in this problem. So this information produced a mean price of $205. So that's our sample statistics. Now we are looking for a 90% confidence interval. So first we are going to get the normalized sigma, the normalized standard deviation. So the normalized standard deviation is the standard deviation divided by the square root of the number of samples, which is 25. We get 9.40. Now, we are going to get the value of z. So our confidence level is 90%. So that's 1 minus alpha. And 1 minus alpha, that means our alpha is 0.1. And 0.1 divided by 2, that is 0.05. So that means the area to the left or to the right is uh, to the extreme left and to the extreme right is 0.05. And from our table, we will get that value as 1.65. So, and then we are now going to plug into our equation. So the interval, our confidence interval is the point estimate plus minus the margin of error, which is z, this 1.65 multiplied by the normalized standard deviation, which is 9.40. So we are just going to add or subtract 15.51 to our parameter. So that means we are 90% confident that the population mean, the average amount of textbooks in the market, that's our population, is between $189.49 to $220.51. So basically, that's how you do a confidence interval. Now, some notes about the confidence interval. So how high is the range of our confidence interval? Generally, we do not want a very, very large range, because if it's a very large range, it's almost, we are going to have a hard time evaluating it if you have a very, very large range. So we want to have a width of the confidence interval that's not too large. But again, if we have a very small width for a confidence interval, we might get an error there, whereas we might not be able to get a good estimate of the true population parameter. So the width of the confidence interval must be of exactly just right. And it depends on the three values: our z, our sample standard deviation, and the number of samples. Sorry, our population standard deviation and the number of samples. However, the population standard deviation is not under our control. So we cannot control what would be the population standard deviation of the parameter that we are studying. And that is why there are only two parameters that we can change here: our z and our n. Now, our z is dependent on the confidence level, because remember, this is from the normal distribution. So if we have a very high z, or we want to have a high confidence level, we would generally have a larger z value. And if we have, and then the other parameter is also the sample size. So our sample size, if you have a large sample size, we can actually limit the width of your confidence interval because it's in the denominator. But if you have a large sample size, expect that you would have a large width of your confidence interval. So that's why for some statistical analysis, having a large sample sizes is actually an ideal situation, or is actually a good thing, because it limits the width. It prevents the width of the confidence interval to becoming too high. At the same time, it doesn't diminish our confidence, our basically our confidence level. Because if we want to have a high confidence level, it's inevitable we would have a high width of interval. And if we have and that is why a large sample size will provide us with, we can limit the width while maintaining our confidence level. So how do we now know what would be our sample size? What's a good sample size? So we can just follow this equation, whereas we have E here as our predetermined margin of error. So we are going to assign first what would be our margin of error. What is our tolerable margin of error, so that we can know how many members of the sample we are going to recruit. So this is z squared times sigma squared divided by e squared. So let's say, for example, an alumni association wants to estimate the mean debt of this year's college graduates. It is known that the population standard deviation of the debt this year's college graduate is 11,800. So the standard deviation of the population is known. So how large a sample should be selected so that the estimate with a 99% confidence level is within 800% of the population mean. So that means our margin of error is 800. So the range must be at around only $800. And we want to have a high confidence, 99% confidence. This is for our estimation of Z. So how do we get that? So our margin of error E is 800 and the value of Z is at 99% confidence level. So that means on both sides, we have 0.005 because 1 minus alpha, 1 minus alpha is 0.99, our alpha is 0.01. Divided by 2, that is 0.0005. And 0.005 is the area beneath the curve. So we are going to look for the Z point, whereas the area beneath the curve is 0.0005. And that value is 2.58. This is from our table, the Z table that we have been using from the previous lectures that we had. And now we have our values as well as the population standard deviation. So we're just plugging it in the equation and we would get a value of 1,449. Now take note that the estimation here that the rounding, we rounded up rather than we round off, because of course we have a decimal point of 0.18 here, so we just round it up to get a whole value of 1,449 rather than round it down. Okay, so the minimum required sample is 1,449. So that is the estimation of the sample sizes, and this is how to estimate our confidence interval if we know the sample standard deviation. So in the next part of the lecture, we will be discussing about what if we do not know the population standard deviation.